Thanks a lot. Let's see, before I get started, raise your hand if you've heard of Kaggle before. Awesome, so I think almost everyone, that makes my job a fair bit easier. Keep my hand up if you have a Kaggle account. Cool, well, maybe 80%. Now keep your hand up if you've made a submission in a Kaggle competition. Keep your hand up if you've written something that we call a Kaggle kernel. 1, 2 people, awesome, thank you. And then keep your hand up if you've come in the top 10 in a Kaggle competition before. Shoot, I was hoping to pawn this talk off to someone else. I guess that's not going to happen. Let's see, so let's go ahead and get started. I'm going to speak with you today about both the future of Kaggle, both where we've come from and where we're going, then how data visualizations will play a larger role within that. So to kick off, our mission is to help the world learn from data, and we see ourselves as operating at the intersection of people, data, and code, and building out software platforms that facilitate the combination of all three of those. And then we got started off on this running supervised machine learning competitions, and that's how many of you first heard of us, where we crowdsource complex machine learning problems to our community of now almost 1 million data scientists from all around the world. And then we're now doing this at scale. Since 2010, we've run almost 250 general machine learning competitions and over 1,000 university classroom competitions. And this has enabled us to attract and grow a really talented and diverse community that's about 60% international, as well as enabled us to teach hundreds of thousands of students machine learning and enable them to learn more about how machine learning works and how it can add value in their products and their daily lives, as well as really to help push the state of the art forward from domains ranging from medical diagnostics to medical imaging to optimizing early stage drug discovery processes to helping enable fields like automated assay scoring. And this has put us in the really fortunate position where we could learn a tremendous amount along the way. This includes what techniques work well from a machine learning and data visualization standpoint, how people win competitions, why our community will participate in competitions, what major pain points people hit right now with the current state of tooling in our field, as well as what we can do to help data scientists and data engineers ameliorate these pain points. And one big message that we've gotten out of our competitions is that great data scientists really optimize the entire end-to-end machine learning workflow, which goes from a business problem to a source data set to splitting a data set and defining a supervised machine learning problem on it, to picking an evaluation metric that they're trying to optimize that hits back at the original business goal or the organizational goal, to extracting relevant features and training models and figuring out how to select the features in the models, and finally implementing this and writing it as a production system, versus focusing exclusively on the machine learning component, which is the component that tends to get the most articles and the most press written about it. On the machine learning component itself, one very strong message we've gotten from our recent competitions is that gradient boosting machines and deep neural networks are incredibly effective at different types of problems. And if you have 2 tools in your chest, these are the 2 tools that you want to use. Gradient boosting machines tend to be very effective at standard problems that look like an Excel spreadsheet or a relational database. And then neural networks are incredibly effective at computer vision or natural language processing problems, or problems that have rich and relatively more unstructured data sets or rich hierarchical data sets. Another high-level lesson that we've learned is model ensembling, where you, instead of just training one model, you train many different models and model types across many different hyperparameters. Almost always ekes out gains. These tend to be on the order of 2% to 5% above what a single kind of best baseline model looks like. So they're almost never revolutionary, but almost always help some. And then that turns it into an engineering decision for, is it worth the cost of maintaining and productionalizing all these models to get this extra performance boost? Another lesson that we've learned is that successful participants avoid overfitting. This is a blog post that one of our users wrote where he was coming in second in a competition right up until the competition ended. Then we split data sets into two sets, a public leaderboard, which tells people their real-time performance over the course of a competition, and a private leaderboard where they only see the results at the end of the competition, and then that's a leaderboard that we use for scoring and for prize money and things like that. And then he was hoping that he would be lucky and be able to go from 2 to 1 on the private leaderboard versus what he saw during the competition on the public leaderboard. And then kept hitting refresh and hitting refresh, waiting for the private leaderboard to be unveiled. Then once it finally got unveiled, he looked at the first spot and he wasn't there. He looked at the second spot and he wasn't there. Then he had to start going down the page and pressing page down before he finally saw himself 50 spots below. And that's because he'd overfit his model to the public leaderboard where he used a lot of the feedback on the public leaderboard as part of the training in his model, and it meant that he made the model look like it was doing much better than it actually was. Needless to say, this was a very painful way to learn about overfitting, and he's never overfit a model like that again. And we've also seen a lot of different pain points in the data science and machine learning and visualization process. Then I see like kind of today's status quo for practices in this area is looking very much like programming in assembly and being decades behind software engineering processes. Some of these pain points, just raise your hand if you've hit some of these. Raise your hand if you've had trouble accessing data that you want to access before. Who's had trouble getting access to high quality data? Who's had trouble cleaning data before and hit a lot of pain points around that? Just some of the stories that we have from there. We have hit like 10 of these for every data set that we host or we put up. For one data set, we've had a lot of planes that landed before they took off because there were some issues with how timing was being labeled and put in the data set. In another data set, we had bulldozers that were manufactured in the year 1000 because someone thought 1000 was a very good missing value to use, and that threw off all the machine learning models that didn't account for that initially. Then another data set that had about 20,000 essays in it, we had a couple essays that read, this essay got good marks, but as far as I can tell, it's gibberish. And that was because a transcriber didn't follow the instructions, which were to discard sets or discard essays that they couldn't read. And they instead put this essay that apparently got a really good score in as this, and that threw off, again, machine learning models that were trained on that and weren't designed to be robust to problems like this. Another issue, how many of people are familiar with data leakage here? Okay, basically, data leakage is a phenomena where your machine learning model learns based on an aspect of the data that wouldn't be available for it to actually make predictions on. It learns based on noise or some other issue in the data instead of real signal that you're looking for. And just one example of this, and this is incredibly prevalent and dominates a lot of different issues in machine learning models. We're working with a data set on prostate cancer surgery that had hundreds and hundreds of features in it. You see a list of the features here. And then when we trained a baseline model on it, we saw this innocuous looking feature called PROS, SURG, popped up as being pretty predictive and very predictive of whether or not a patient had prostate cancer. And it turns out when we dug a little deeper, it stood for the patient had surgery to correct for prostate cancer. So it's the type of thing that is incredibly useless if you're trying to apply it in a clinical setting or in a real-world setting, but can trick machine learning models and trick you to think that if you're not being robust to it, you're getting a much better performance than you are. Another pain point we've seen is going from research to production can be incredibly brutal. Things tend to take about twice as long to productionize as a lot of companies think they will, and many times they made a mistake in the model training or the model validation process, and when they put a system in production, it actually hurts their performance instead of helps their performance on the product or business metric they're tracking. And then finally, probably the biggest pain point that we've hit is around reproducing others' work. Who here has had trouble trying to reproduce a data visualization or code that someone else has created? Yep, so almost everyone, most people it looks like. In principle, this should be something that shouldn't take any time at all. It should be completely seamless to reproduce others. In practice, it takes days to months to actually do it. And then our viewpoint is that with a set of open source tools that are currently out there, we can stitch them together in a way to be a lot better than this, based on a couple different principles. First, accessing data should be really seamless. It should be quick and easy to find the data that you're looking for and need to access instead of having a lot of red tape in the way. Secondly, you should never have to reproduce or redo work that others have done, except if you're trying to learn something about it or if it's helpful for your own learning to go through something that someone else has done before. And instead, it should be easy to take what others have done and build on top of it. Another principle is a single command should be able to reproduce everything someone else has done, start to end, and not starting off with a complicated README file or a long document where you have to follow 20 different steps to do the same thing that they did before. We also think making a successful one-line update to a data pipeline or a data visualization should take seconds, even if it's as part of a system that kicks off 1,000 hours of compute downstream to it. And then finally, we think helpful metadata shouldn't stay buried in mines or emails, but should be surfaced alongside the data where it's relevant to you, and you should be alerted to issues with columns or fields as you read them in. As well as that, best practices for analytics, machine learning, and data visualization should be set up to be really easy defaults and not complicated custom contraptions that individuals or teams have to build out and be aware of. So we're doing a couple things to try changing this. And I'll give a quick demo of some of the work that we're doing in this area. Let's see if my internet connection is going to work. So I'm going to start off with one of the machine learning competitions that we first got known for hosting. And about a year and a half ago, we launched a new section to this competition. But before I go into that, a pattern that we'd seen early on in competitions, and on the order of 2 to 5 or 2 to 6 forum posts will be made in each competition where someone was sharing, like, here's a Python model to help get it started for this competition, or here's a PNG file for this graph I made of the data, and here's the Python code I used to make it. Then almost inevitably, the next 10 forum posts would look like, which version of Python did you use? Why want this library work? I'm hitting this error, things like that. So people were having a really tough time using code that others were sharing. Then we launched a product called Kernels, which, just to drop into it quickly, makes it really fast and easy to spin up a script or notebook or file on the relevant data. In this case, I can click through, I can see a quick preview of the data set. In this case, it's a duplicate question competition we're working on with Quora, so it has pairs of questions, then a binary flag marking whether or not they're duplicate. And then it's quick and easy to read into the data sets, then have access to a Python Docker container that has all of the libraries I normally need to work with this data pre-installed in it. And one unique thing that we did in this environment is we required everything done in this environment to be made public immediately. And that had the side effect of creating a really strong culture of sharing and collaboration on Kaggle. We're now, for a given competition, instead of 5 to 6 different code examples being shared on it, we now see on the order of 500 to 1,000 different code examples being shared on it, along with a lot of back and forth from the community and a lot of people forking and expanding on the kernels that get shared. The next step in this is we launched an open data platform called Kaggle Datasets, where we want to take some of the lessons that we learned from competitions and really expand on those and make data much easier to access and for people to collaborate on. So one example of that I'll just pull up is a data set published by a governmental organization on 2015 traffic fatalities. And then the status quo for organizations or users publishing data historically is they'll just take a data set, throw it up as a CSV file or a set of Excel documents online on a stack web page, and then if you're really lucky, they might document some information about it, but that tends to be really hit or miss. So we provide a way to quickly download the data set as well, but we just see that as like the baseline prerequisite. And then the other things that we're doing on top of this is trying to make the data set more and more valuable to people who access it, and as more people use it, to make it more valuable to everyone who comes after them. So one example of this, in this case, this person who created this data set used kind of poor, obscure naming of columns. For example, I have no idea what PDS means or PRNOT MVIT means. But unfortunately, someone else came along and was able to edit this and add a human written label on top of it that this is the number of people that were involved in the collision, but were not in a motor vehicle. So this is the number of passengers that were in here. And that makes it a lot easier to understand what a column means or what individual fields in a data set means instead of having to dig through a large set of government documentation on the data set. The most powerful thing that we do for this is we capture code that's been written on the data sets in an easily explorable way. So as people are exploring this data set, they're sharing the code back to the community, and then it's a quick way for me to go through and see what other users have done on this data set. It looks like this user mapped out some fatalities. It's not a surprise given that they did a map that looks like a population map of the US. So I'm just going to see if there's, and this is also looking at the impact of weather and drunk driving on the data set. So this type of thing means that when I want to go and work with this data set, my starting point is in an empty screen or a blank cursor and no idea what people have done before on it, but instead I can have all the different code that people have written before in this data set as a starting point, which could inspire my own work. It saves me the trouble of rewriting the functions to read the data set into Python or R, my favorite compute language, and it makes it a lot easier to go and extend that. So then I'm going to swap back to the presentation. So that's a quick overview of where we are right now. Then as some of you may know, others may not, about 7 weeks ago, we announced that we recently joined Google Cloud to accelerate our growth and enable us to work much faster into building out datasets, kernels, and Kaggle competitions. First, right now we have about 500 datasets available through Kaggle Datasets. Our goal is to have every publicly accessible dataset in the world available through that long term, and really to grow that to make a simple common interface for accessing the world's data, as well as capturing all the important code and metadata on top of that to make your lives as data scientists or data visualization engineers much easier. To provide a central searchable hub of organizations' data and have the starting point for make it really easy to figure out once you're within an organization what data sets you have available to work with. And then finally, we see the products I mentioned earlier called Kernels as a nice UI around a set of open source primitives that combines version code, version data, and a version computational environment through Docker containers to create a reproducible result. Out of curiosity, who here's used Docker before or used Docker directly? Couple people. For those that haven't, and for those of you that are working in Python or R versus Tableau or more point-and-click GUIs, I really recommend working within Docker for your own work. It provides a much easier way for you to keep track of the environment that you're working with and go back to a previous point in time in that, and it'll really save a lot of time. Let's see, then the final piece for Kaggle is we've started writing code competitions where people submit code, not data, to our platform. And we see this as enabling a large number of exciting new competition formats in the future, including back-tested time series, live data feeds, reinforcement learning, generative and adversarial learning competitions, as well as machine learning under computational constraints, and finally competitions around sensitive data sets. So I'm going to go ahead and open this up for questions now, and thanks a lot for taking the time to listen to me. Let's see, raise your hand if you have any questions. Pass that around.
The question is very simple, basically. So how does Kaggle make money?
I have this mic too, I'll pass it around. Historically, so.
Who are your?
Yeah. Historically, we've had two revenue streams. People pay us to host competition, so that organization sponsoring the competition, putting up prize money, also pay Kaggle to do that. And then secondly, we have a jobs board for data scientists that we actually initially didn't charge revenue for that or charge to post on it. Then we quickly saw that we had a quality problem where a lot of people were posting a lot of crappy jobs to that. Then we started charging for that more as a way to do quality control. And it turned out that ended up being a nice revenue generator for us as well.
So there was a lot of information that you gave, and I noticed that you have a course on Udacity, on prepping up for a Kaggle competition. So what would you recommend for people, sort of trying to get their feet wet and also to do well?
Let's see, I think there's a lot of really good resources out there and a lot of ways to get your feet wet with machine learning right now. My biggest recommendation is to find a project that you're interested in solving, whether it's something that's publicly available online or like if you have a pet project, and then collecting data, making sure the data is available for that, and trying to train a baseline model and trying to improve that model on that. So starting more from like a project-oriented basis instead of here's a set, I want to learn about neural networks and checking that box, or I want to learn about gradient boosting machines and checking that box.
Hi. So one of the things I noticed with Kaggle was that everything is about how you can get your score a little bit better than everybody else. So everything is focused on getting to the maximum score you can get. Often I find myself realizing that often the value of data science is mostly just in the framing of the problem and getting things started, and the extra incremental 0.01% on the score isn't the biggest value. Are you planning to do anything that will accelerate the number of projects that can be tackled by the Kaggle platform with a less of an emphasis on the end score?
Yes, absolutely. So that was the motivation for launching the Open Data Platform and also the Reproducible Kernels environment when we launched those, as well as we're incentivizing our community to contribute on those aspects as well. And more generally, I completely agree with for a lot of different problems, the value is going from not using machine learning to using machine learning versus figuring out how to get the extra 5 to 10% of value in there that you can by really trying to optimize the approach, especially for a lot of startups or a lot of smaller businesses. And then there are a number of valuable problems from quant finance to many large-scale internet properties where that extra couple percentage boost is really, really, really valuable too. So it really is like a very problem-specific context for which pieces of it's valuable. And I think our most interesting competitions are the ones where we enable people to work on that full end-to-end pipeline instead of kind of narrowly on the machine learning component. So there's a lot of raw unstructured data to work with, and they have to figure out how do they want to go about using that, incorporating that. And that isn't, in many cases, isn't at all obvious, and that's where the people who spend the time there and do a good job there are those that ultimately win.
Yeah, so I have two questions. One is, again, similar to what the previous question was. I'm not really interested in optimizing to the nth level. It's just trying to get at understanding of the tools and the process to solve a problem, right? So things like, and for somebody out there, there's so many things out there, fast AI, there's a whole bunch of things out there. So what would you recommend as the easiest way to kind of get started on a machine learning project? Because I do have one, right? And is it just the kernel? Is it fast AI? Is it going through, you know, a bunch of courses? And I know this is not specific to Kaggle, but just wanted to get your thoughts on that.
Yeah, so I'd say what we're at Kaggle are good at right now is we're good at offering a set of use cases or set of projects that people would find interesting to apply machine learning on. Then beyond that, I think fast AI is a good option. There's a lot of other good courses out there. So I'd pick, if there's like an instruction style that resonates with you, I'd pick that one and go with that.
I had a question more on the data side. So I come from the world of remote sensing, Earth observation, and I've seen some Kaggle competitions on that topic, obviously. But the strategy of having data sets that are fully discrete covers part of the space. I'm wondering if you've thought about adapters or API or other ways to get access to more of the world's data into a data science framework, but data that may or may not want to live there kind of permanently and exclusively.
What was the last bit of your question? The echo is making it a bit tough for me to hear.
So have you guys thought about adapters or APIs or other kind of mechanisms for hooking up to data that needs or wants to live elsewhere, but making it searchable and accessible through your platform, usable, but not necessarily hosting it or living there?
Yeah, that's one thing that we definitely want to do in the future, and it's on my roadmap. I don't have a specific timing for that, though. But the question was, how do we plan to work with data that can't necessarily be made public as flat files, but naturally lives in other systems, whether it's our, say, relational database, Salesforce data, that behind their product, or anything else like that.
Hi, I was just wondering, as you do more and more of these competitions, do you envision a point where you can actually use these competition entries and the results to generate de novo solutions to new competitions programmatically, where the sort of training data is how well the sort of posted solution does on the problem, and with sort of the input being that actual code? Basically replace all the Kaggle competitors with a AI Kaggle competitor.
So again, I'm having a bit of a tough time hearing because of the echo, but if I gather correctly, your question was, how does, can we leverage all the data that we've gotten on which methods work well in Kaggle in competitions and how those perform to then predict which methods will work well on new competitions that we host? I think there's a lot of really fascinating work that's being done on this from it's academically, it's under the kind of moniker learning to learn, or can you train a model that then comes back with a set of hyperparameters and models or pipelines that's likely to work well on this new machine learning problem that you've seen, and maybe with some metadata about the machine learning problem, but not having tried training a model on it so far. So I think it's something that we've started doing just by simply sharing back what works well to our community. A lot of people have kind of learned from a manual basis that way, and there's a lot more that we can do here in the future for surfacing more granular data about that can be used directly. But I think that overall, as time progresses, the tools for data scientists to train or optimize machine learning models will start operating at higher levels in the sense where it's mostly focusing on the part that can be automated. So things like this type of data should feed into this problem, this shouldn't, or this is not going to be predictive of the future because it doesn't have a causal relation, or components like that, versus the underlying engineering work to train and optimize machine learning models. Thanks a lot.